So hi guys, I'm back with a new video, and for this video I'm going to summarize this given chapter, which is the chapter 8. So let's proceed. The subnetting IP networks. So designing, implementing and managing an effective IP addressing plan ensures that network can operate effectively and efficiently. This is especially true as the number of the host connections to the network increase. So, broadcast domains. In an Ethernet LAN, devices uses broadcast to locate other devices and the services. Other devices is a device uses address resolution protocol or the ARP, which sends the layer 2 broadcast to an unknown IPv4 address on the local network to discover the associated MAC address. Services, in the other hand, is a host typically acquired the IPv4 address configuration using the Dynamic Host Configuration Protocol or the DHCP, which is the one that sends the broadcast on the local network to locate the DHCP server. Problems with large broadcast domains. Uh, a large broadcast domain is a network that connects many hosts. A problem with the large broadcast domain is that these hosts can generate excessive broadcasts and negatively affect the network. So, LAN 1 connects 400 users that could generate broadcast traffic resulting in slow network operation due to significant amount of traffic, and it can cause the slow device operation because a device must accept and process each broadcast packet. Octet boundaries. Every interface on the router is connected to a network. The IPv4 address and subnet mask configured on the router interface are used to identify the specific broadcast domain. Recall that the prefix length and the subnet mask are different ways of identifying the network portion of address. Subnetting on the octet boundary. To understand how subnetting on the octet boundary can be useful, consider the following example. Assume an enterprise has chosen the private address .10.0.0.0/8 as its internal network address. That network address can connect 16,777,214 hosts in one broadcast domain. So obviously, this is not ideal. The classless subnetting example. To understand how subnetting a classless level can be useful, consider the following examples. Consider the private network address 192.168.1.0/24. The first three octets are displayed in decimal, while the last octet is displayed in binary. So the reason for this is because that we will borrowing bits from the last octet to create subnets of the 192.168.1.0/24 network. So subnetting formulas. To calculate the number of subnet that can be created uh, from the bits borrowed, use the formula and display the possible number of subnets that can be created when borrowing 1, 2, 3, 4, 5, or 6 bits. So take note that the last 2 bits cannot be borrowed from the last octet because there will be no host addresses available. So therefore, the longest prefix length possible when subnetting is the /30 or 255.255.255.252. Creating for subnets. Now consider the network topology. The enterprise is using the private network address 192.168.1.0/24. Range in requires 3 subnets, borrowing a single bit only provided 2 subnets. Therefore, another host bits must be borrowed using the 2n formula for 2 borrowed bits results in 2 subnet 2 is equal to 4 subnets. So creating 100 subnets in a 16 network. So consider a large enterprise that requires at least 100 subnets and has chosen to private addresses 172.116.0/16 as its internal network address. So when borrowing bits from its 16 address, start borrowing bits in the third octet, going from left to right, borrow a single bit at a time until the number of bits necessary to create 100 subnet is reached. Calculating the host. To calculate the number of hosts each subnet can support, examine the third and fourth octet. After borrowing 7 bits of the subnet, there is 1 host bit remaining in the third octet and 8 host bits remaining in the fourth octet for a total of 9 bits that were not borrowed. Subnetting based on host requirements. There are two considerations when planning subnets. So the first one is the subnet host address requires for each network, and the second one is the number of individual subnets needed. Traditional subnetting waste addresses. Using traditional subnetting, the same number of addresses is allocated for each subnet. If all the subnets have the same requirements for the number of hosts, this fixed uh, this fixed size address blocks would be efficient. However, most often that is not the case. So, for example, require 7 subnets for each of the 4 LANs and 1 for each of the 3 WANs connection between routers. So, using the traditional subnetting with the given address of 192.168.20.0/24 bits can be borrowed from the host portion in the last octet to meet the subnet requirements of 7 subnet. Variable length subnet mask. So in all of these previous examples of subnetting, notice that the same subnet mask was applied for all subnets. This means that each subnet has the same number of available host addresses. So traditional subnetting creates the subnets of equal size. Each subnet in the traditional scheme uses the same subnet mask. So it allows a network space to be divided into unequal parts with VLSM. The subnet mask will vary depending on how many bits have been borrowed for a particular subnet, thus the variable part of the VLSM. The basic VLSM. To better understand the VLSM process, you can go back to the previous example. So the network 192.168.20.0/24 was subnetted into 8 equal sizes. So 7 of 8 subnets were allocated. 4 subnets were used for the LANs and 3 subnets for the WAN connection between the routers. Recall that the waste address space was the subnet used for the WAN connection because those subnets required only 2 usable addresses, so one for each router interface. To avoid this waste, VLSM can be used to create smallest subnet to the network connection. The VLSM chart. An addressing chart can be used to identify which block of addresses are available for use and which ones are already assigned. So this method tips to prevent assigning addresses that have already been allocated. So the network address planning. So the allocation of network layer address space within the corporate network needs to be well designed. So address assignment should not be random. For the assigning destination to device, within a network, there are different types of device that requires address including the end user client, the servers and peripherals. servers that are accessible from the internet, intermediary devices, and the gateway. So the IPv6 global unicast address, subnetting requires a different approach. The same reason for subnetting IPv4 address space in order to manage network traffic also apply the IPv6. So subnetting using the subnet ID. The 16-bit subnet ID section of the IPv6 global unicast address can be used by any organization to create internal subnets. So the subnet ID provides more than enough subnets, and host support then will never be needed in one subnet. For instance, the 16 bits can be created up to 65,536 to 64 subnets. This does not include the possibility of borrowing any bits from the interface ID of the address, and it supports the 18 quintillion host IPv6 address per subnet. So the IPv6 subnet allocation with over 65,000 subnet to those from the task, the network administrator becomes one of the designing logical scheme to address the network. So that's all for this given chapter number 8, and I hope you like it. So thank you for watching.